Below is a back-to-back stem plot with split stems showing how many points were scored by the world-renowned Dallas Cowboys and their opponents during the 2014 to 2017 season. So that was 48 regular season games. So the Cowboys are on the left. The opponents are on the right. We do have a key, which is extremely important when you have a stem plot. So 2/0 is 20 points were scored during the game. All right. So let me ask you a couple questions. Make sure you guys understand how to read this. What is the lowest number of points that an opponent scored in a game? 0. What is the highest number of points that an opponent scored? 42. What's the lowest number of points that the Cowboys scored in a game during that time? 6. Notice that there is not a 0 for the Cowboys because they don't ever put up 0 points. They're always scoring. Hello. And then what's the highest number of points for the Cowboys? 42. Very good. All right. Now we can, do you see it? So 42. So it's 40 and 42 there. Okay. All right. What was the Cowboys' highest scoring game? We just said that. What's the answer?
42.
B, 42. Very good. The answer is 42. Awesome. All right. Ignoring the outliers, what is the shape of the opponent's distribution? So what they're asking you to do is ignore these guys right here. What is the shape of that distribution?
Right.
Yep, I would agree. That is skewed to the right. Skewed to the right. Very good. Now, what is the center of the opponent's distribution? What is it close to? So you can do the whole marking off thing. So we got 10 and 10 and 10 All right, what do you think? 19. I would agree. Do you guys have any questions on how to read a back-to-back stem plot? It's easy, right? Here is where the challenge is. What shape is the Cowboys' distribution? It is definitely bimodal. Absolutely. Very good. All right, cool. What if, just for funsies, the Cowboys' distribution looked like that? Obviously it doesn't, but what would that shape be? Not skewed right.
What?
Why not? You see why? If I look at it this way, that's from highest to lowest. And whenever I'm looking at shape, I always need to be looking from lowest to highest. So when you look at it this way, this one is always good. This is always weird. You look at it this way, and then you have to think about flipping it this way. So it's all down. It's all messed up, right? Because we gotta look from low to high. Low to high. Okay? So from low, the skewed data is on the low end, and there's most data would be at the high end. So from low to high, the skew is on the left, actually, if it had looked like that. So that one's always a little tricky. Just be careful whenever you're doing that. Got it?
Like your foot.
It has to be lowest to highest.
Yeah, that's what she drew.
I'm done asking questions.
Oh, please do. Please do.
Basically, just look at your feet and go out. Yeah, you got it.
Look,
Yeah.
here's the thing.
So that has left.
Look at your feet.
Preferably with shoes. Yeah.
All right, what are some important things to remember when you are making a stem plot?
Make sure.
Must include a key. The number one reason that people do not get 100 on the first test is because they leave a key off their stem plot. What nerds?
How dare they?
How dare they? Actually, if they were nerds, they wouldn't forget it. I'm just teasing. All right, so make sure you guys are remembering your key, all right? Another important thing about stem plots is a key must be included. That's another important thing about stem plots. The number one reason that people don't get 100 on the first quiz is because they forget their key on their stem plot. What's another important thing when making a stem plot?
You must be on the paper.
Don't forget the key. God bless America. It would seem like this is important for some reason. I don't know.
I mean, there are exclamation points for everyone.
Oh, it didn't do it. Hate technology. School technology. Anyways, I highlighted the word key. All right, you guys got it? What are you never going to forget?
The key.
A key, a key. Okay, all right. Cool. Oh, I'm forgetting a key, Miss Lakey. It ain't happening. All right, histograms. Have you guys ever seen a histogram before in your life?
Yeah.
What's a histogram? Something about history? Oh, wow. Yikes. Okay. So the following table represents the number of free throws made for the Sweet 16 NCAA teams from 2019. All right, so we've got our free throws made, and we need to make a histogram. So, first thing, step one. What is the lowest value? What is the lowest value in the data set?
Michigan.
406. Perfect. Number two, what's the highest value in the data set? 635? All right. Number three, we need to decide on a scale for the x-axis. Okay, I don't want a dot plot. A dot plot would show each individual number, and I don't want that. I want a histogram. What a histogram is going to do is it's going to kind of put things in a group, right? So I need to get from about 400 to about 650-ish, all right? And I want to have somewhere between 5 and 10 bars on my histogram, okay? So don't write this down yet, right? So here's the deal. I need to get from about 400 to about 650. Don't write this down yet. If I were to go by like 20s, then 420, 440, 460, 480. Can you see that would give me a little too many bars, right? That's going to be too many. I'm going to have like a bar here, bar here, bar here, bar here, bar here. Like now I've got too many bars, and that's going to be why? Why am I doing that? So that's a stupid idea. All right, so how can I get from about 400 to about 650 and have somewhere between 5 and 10 categories to put things into?
50.
By 50s? That sounds a little better. Okay, I like it. So we're probably going to go by 50s. So we need to make basically a frequency table. We need to go from 400 to 449. Then we need to go from 450 to 499. And then we need to go from 500 to 549. And then we need to go 550 to 599, 600 to 649. Do you see that we would then have about 5 bars there? So 50 looks like it was pretty good. So in our data, I need to find out how many teams had somewhere between 400 and 449 free throws made. How many you got? 2? 2. 2? Does everyone agree on 2? All right, so we got 2. How many teams had between 450 and 499? 4? Everybody agree on 4? 4. How many between 500 and 549? 3? 2? 3? 2? 3? 2?
You said 3.
No, we're just like tallying down.
Basically, we're just kind of trying to see how many are in each of these categories here. So,
Do like dashes. Just like,
okay, yeah, for sure. That's a great idea too. Look at that. So we could do that. Like we could be like 450 would go here, and then 603 would go here, and then like 461 would go like here, and then like 579 would go like here. Oh, that's a great idea. Wasn't this a great idea? Do you see what we're doing here? 461, 490. Yeah, we're doing like little tally marks. Yeah, because you guys are so good at tally marks, we just like doing them. 635, 560, 509. Oh, yeah. See, this was such a great idea. I'm so glad you came up with this. 541, 551. 449. Okay, there we go. So we had 2, 4, 3, 4, 2, 3. I can read 3. Okay, cool. All right, what do you guys think we do now? Actually make the graph, right? So I'm going to have my x-axis here. And I'm going to start at 400. Now, what will my next line, what will my next value be on the graph here? Nope. 450. Okay, very good. 450, and then 500. 550. Whoa, did you just say this is like a bar graph?
Yeah.
Whoa.
Bar graphs are for what kind of data? Categorical. Histograms are for quantitative data. Also, we're going to talk about the how they are the same and different and all that fun stuff. All right, my y-axis. What's going to go on the y-axis here?
1 through 4.
1 through 4, and what does that stand for?
Are the number of teams on
The number of teams, right? All right, so we've got 1, 2, 3, and 4. And this is the number of teams. And the x-axis was free throws made. Okay? Everybody good? How tall does the 400 to 450 bar need to be? 2. Now, these bars touch. Different than a bar graph. Bar graphs, the bars don't touch. These bars do touch. 450 to 500, I need it to go as tall as 4. And then 3. And then 4. And then 3. There's histogram. Cool, right? Now,
Histogram with the bars touch, but bar graphs they don't touch.
correct? Now, why are these bars touching?
Because they're
It's like a
close
range.
numbers.
Very good. So it's because this is quantitative data that like it literally this bar right here, this first bar right here, this bar is from 400 to what? Technically, it's to 449.9999999, but these are only integers, right? So this first bar is from 400 right up to 450, and then we go right into the next bar, 450 right up to 500, and then we go into the next bar, 500 right up to 550. Okay, so it's like it's a values that never really have a stopping point. There's never a gap. With a bar chart, again, I can put the bars in any order I want to. There's not like a seamless transition from one to the next. It's not a certain number or a number line. It's just categories down here. That's why the bars don't touch, is so you don't think that they are seamlessly going right up to the next one. The histogram, that's why they do touch, because they are a continuous number line. Does that make sense? Do you guys have any questions? What? A line graph? That is a thing, yes. A line graph is a thing, but what do you mean by that?
Like, could you do the same data with a line graph?
You could do this data with a line graph. Line graphs are very specialized. Like, I'm surprised you know about a line graph. They're like, not very many people use a line graph.
What's a line graph?
It's almost like you just put you put dots in places and you just connect the dots.
I'm smart.
I've been using that since like 3rd grade. Yeah, that's like the basics.
My bad. I'm just not cultured, I guess. Yeah, no, I'm actually serious that not very many statisticians use line graphs.
Because I was going to say, it's actually like all I'm saying a statistician.
A statistician?
A statistician.
Oh, yeah. Oh, yeah. So making sure we do not confuse them. Histograms are for what kind of data? Quantitative. And what is very obvious about a histogram when you look at it? About its bars. They touch. Okay? The bars touch. All right. A bar graph, however, is what kind of data? If you could just think, that would be really great. Bar graphs are categorical or qualitative. I'm not going to say that qualitative is not a word, but categorical. And what else is true about their bars? Bars do not touch.
Thanks, Dawson.
Cool?
Histographs and bar graphs.
Histographs and bargrams? Okay, got it. Next! We need to use percents or proportions instead of frequencies, also known as counts, on the vertical axis when we are comparing distributions that have a different number of observations. Here's what I am talking about right here. This is 2 histograms. One of them is showing the word length in a medical journal. One of them is showing the word length in a magazine. What do you guys think is going to be true about the words in a journal, a medical journal? They're going to be bigger, longer words, right? In a magazine, you're going to have little short words, right? So the fact that these are showing us that there's 90 3-letter words and 30 4-letter words and blah, blah, blah. Over here, we don't have very many 4-letter words, right? But why not? There's not as many words in general in a magazine. So we put it on a percentage basis, and now look, there is a larger percent of 3-letter words in a magazine than there are in a journal. Because again, journals are going to have longer words usually anyway. The magazine's just going to have little short little words with their little pictures. Okay? So we want to make sure that we use percent when comparing distributions. We want to be very careful about this, and we want to use percents when comparing distributions. That's that whole thing about remember the chocolate ice cream graph from the other day, right? And we had more males like chocolate than more females like chocolate than males. It looked like more females like vanilla than males, but when we put them on a percentage, we could see that actually the male percentage was higher. Okay? So we got to make sure we are comparing percentages. All right. Just because a graph looks nice doesn't make it meaningful. This looks pretty, doesn't it? Lots of pretty little bars. This is your each student. We've basically given each student a number, right? I number you off. And I say, hey, how many letters are in your name? Student number 1 has a 7-letter name. Student number 2 has a 4-letter name. Student number 3 has a 4-letter name. Like, why? What's the point here? Okay? So the point here really doesn't help me. I could just write your names out and see who has the longest name. Student number 7, 8, whatever. This is not very meaningful. It doesn't summarize the data. Over here, now I've got a summary. I can see that 4-letter names are more frequent than 5 or 6-letter names, okay? So we want to use graphs to summarize data, okay? Use graphs to summarize data. All right. Everybody good? Here's your last question of the 1.2 notes. Imagine taking a random sample of 60 students from McKinney Boyd, and we're asking them about their birth month. Should you use a bar graph or a histogram to display this data? Why? You tell me, what is it?
Definitely a bar graph.
Why are we going to use a bar graph?
The swap categorical.
Tell me how we could use a histogram.
We have a histogram for each month. I know it's a lot more work, but it can be done.
Days
Seems
of
like
the
it would.
birthday, February.
January.
That's all my stars.
But even then,